So now that we've completed the Desmos lab, let's sort of summarize what happened. So notice that we have this connection between zeros or roots and the factorization of the polynomial, right? So we saw that if x equals a was a 0, right, then that would lead us to a factor of x minus a in the polynomial, right? Because a replacing x would give us a minus a is 0, right? So that gives us a 0. So all of this is meant to be sort of 4 different ways to talk about the same feature of the graph, right? If you let x equal a, it's going to give you 0. It's going to therefore be x equals a is a solution to the polynomial f of x equals 0. X minus a is a factor, and a comma 0 is an x-intercept. Okay, and what you were hopefully understanding from the end of the Desmos lab is this idea of repeated zeros, right? In that last example, which we'll look at in a second, we had an x minus 2 squared, right? So we look at the exponent of the repeated 0, we call that the multiplicity. That's the multiplicity of the root or the 0. When the multiplicity is odd, including to the first power, right? So this is what we were mostly looking at the beginning. When the multiplicity is odd, the graph just crosses through the x-axis, right? So you're going to have it just actually cross through at a. But when k is even, the graph will just touch, sort of skim the x-axis and bounce back off. So instead of passing through, it might sort of touch and then bounce back off. So that's what we were saying. So this is what it would look like if we have odd multiplicity, and this is what it's going to look like if we have even multiplicity. Okay, so looking back at that example from the Desmos lab, we saw that this x minus 2 here leads us to this behavior of the function just bouncing off. Oh, my computer is giving me some sort of warning. Okay, closed it. We're back. So let's put this into action. So we want to find all the zeros for the polynomial p of x equals negative 2x to the fourth plus 18x squared. So if we're going to try to find the zeros, we want to take full advantage of the factored form of p. So this section is going to be a big test of your factoring skills. So if you know that you're kind of weak with factoring, then that's a skill you're going to need to refresh your memory with. In particular, you should be able to factor greatest common factors, which is what we're going to do here. You should be able to factor trinomials. You should be able to factor a difference of perfect squares, factor by grouping. Okay, so all of those are things you should look up and make sure you understand. So let's look at how we'd factor this. First thing I am going to look for is the greatest common factor. So p of x is going to be equal to, the GCF is either negative 2x squared or positive, we'll talk about both. So if I pull out negative 2x squared, then I'm left with a positive x squared and a minus 9 here. Or if I just factor out 2x squared, then I'd be left with a negative x squared plus 9. Okay, both of these are actually an okay start. If I write it this way, then I could see my difference of perfect squares here. So this is a little formula for you to be reminded. Factoring a difference of perfect squares looks like this. So in this case, we're going to do x minus 3 times x plus 3. Now if I factor over here, I still actually have a difference of perfect squares. It just would be thought of as 9 minus x squared, right? Because the 9 is positive, the x squared is negative. So if I factor that as a difference of squares, it would be 3 minus x, 3 plus x. Both ways, when we try to now solve the equation when we set it equal to 0. So remember back up here, right, that we know that the 0 is going to be a solution to the polynomial equation f of x equals 0. So if I set this polynomial equal to 0, right, then I know that this is going to give me my roots. So the zero product property, I'm going to write that name down over here just in case that's something that you need to look up. Zero product property we've talked about in class. This is something special about 0. It says that if I know I have the product of 3 different factors and the result is 0, it must be that either that first factor is equal to 0, or the second factor is equal to 0, or the third factor is equal to 0. And when I set each one of these factors equal to 0, I get 3 individual little equations to solve. Solving for x here, I would divide both sides by negative 2 and still get that x squared equals 0. Oops, I don't know why that happened. And so x would just equal 0. Let's note here, though, that because this was x squared equals 0, this 0 has multiplicity 2. Over here, adding 3 to both sides, I get x equals positive 3, and subtracting 3 from both sides here, I get x equals negative 3. So I have 1 root, 2 roots, 3 roots, this one with multiplicity 2 and the other two with multiplicity 1. So what would this look like? Well, I don't know exactly what it looks like, but I do know that it's going to have a 0 at 0, 1 at 3, oops, not very well spaced, and 1 at negative 3. And I know that the multiplicity at 0 is even. So the function is going to pass through at both negative 3 and 3, but it's going to just skim. But I don't know if it's going to look like, okay, pass through, skim, pass through, right? Maybe it looks like that. Or maybe it looks like pass through, skim, pass through, right? I don't know which one of these it will be. So this leads us, of course, to what we talk about next year. So this is the leading coefficient test is useful for this. Get this summary. So, oops, went bar. When n is odd, the degree of the polynomial is odd. We have two cases. Notice that the polynomial ends in opposite directions when it's odd, right? So one part goes down towards negative infinity, the other one goes towards positive infinity. That's when it's odd. When it's even, both head off towards positive infinity or both head off towards negative infinity. Okay, and the dashed lines in between means we don't really know what it looks like in between. Now, further, if the leading coefficient, so the leading coefficient, what does that even mean? Leading coefficient is, so let's define this. Leading coefficient is the coefficient, or the number in front of the highest degree term. So looking at this last example, I've got two terms, negative 2x to the fourth and 18x squared. X to the fourth is the higher degree term, so my leading coefficient is this negative 2 here. Okay, so if the leading coefficient is positive, we see that it's going to have this sort of shape. If the leading coefficient is negative, it have this shape. And then for even, likewise. So in this case, for the last example we were just looking at, we were looking at an even polynomial, fourth degree. And we have that the leading coefficient is negative. So this tells us that the ends are going to be going down. So which one is right? Is the blue graph right or the green graph right? So of course it's the blue graph, right? Because it has to end going down, right? So it has to end it going down in both directions. Okay, so let's practice this a little bit more. Let's look at another example. If we want to find all of the zeros, we have to go ahead and factor this, right? So ideally, I would have you pause the video and see how well you can factor this polynomial on your own, since officially that is something that you learned in high school or Math 100. So start by finding a greatest common factor, then you'll be left with a trinomial, and try to actually factor this on your own. So pause it and go ahead and do that now. Okay, so hopefully you paused it. This is the first step. I factored out the greatest common factor, and I'm still left with a quadratic here. So this is a trinomial. By the way, I should just point out here that a common mistake when you're factoring out all of some factor that you might accidentally drop this term, but you do need to keep the +1 here to hold the place. Remember, this was a trinomial to begin with. It has to stay a trinomial. If I were to distribute this back out, that would undo what I did for factoring. Okay, so now I have this trinomial, and I need to try to factor it if possible. By the way, if I can't factor it when I go to solve this equation, I would just use quadratic formula on this trinomial. But this does factor further. In fact, it factors as 2x plus 1 quantity squared, and hopefully you got that on your own. So now to find the zeros, we want to solve where the function is equal to 0. And so our two possibilities are either 3x cubed equals 0 or 2x plus 1 equals 0. Noting that here we have a 0 of multiplicity 3 and here a multiplicity 0 of multiplicity 2. So solving for x, I get 0, and here I get x equals negative 1/2. So what is this going to look like? Well, I know it has its zeros at negative 1/2 and 0. Because this is an odd multiplicity, it's going to just pass through the graph at 0, but it's going to bounce off and sort of skim the surface of the x-axis at x equals negative 1/2. There's one other fact we need to look at, and that is that the leading coefficient here is 12, and that is for a polynomial of odd degree. So we go back and look at what happens. So we're looking at a polynomial of odd degree. Oops, sorry. I don't know what I just did. Okay, we're back. So we got polynomial of odd degree, and our leading coefficient in this case is positive. So we're looking at the end behavior to start going down way towards negative infinity and end heading up towards positive infinity. Oops, hold on. Okay, we're back, so I had to fix my screen. Okay, so we know it's going to be starting heading down towards negative infinity. It's going to skim the x-axis at -1/2 and then pass through the x-axis at 0. So it's going to look something like that. Okay, let's look at another example. We've got p of x equals x to the 5th minus 16x. Again, take a moment to pause this and factor. So hopefully you found the GCF and were able to notice that this is a difference of perfect squares, x squared plus 4, x squared minus 4. But further, this is again a difference of perfect squares. So we can factor this completely as x plus 2, x minus 2 here. We cannot factor a difference of a sum of different, we cannot factor a sum of perfect squares. So that's what we've got here. So now to find the zeros, we set equal to 0, and now we've got 4 possibilities. So either x is 0, x squared plus 4 is 0, x plus 2 is 0, or x minus 2 is 0. That's by the zero product property. So here we get just 0, and that's with multiplicity 1. Here, if I try to solve for x, so I would be subtracting 4 from both sides. And now I get x squared equals -4. So how can you think of a number that when you square it, you get -4, right? If I were solving, x would equal plus or minus the square root of -4. That's a plus. So that's plus or minus 2i for those of you that remember imaginary numbers. But for our purposes, there's just no real number. We're not going to see this on the x-axis. We don't see it. So that one is not a real root. Over here, we're getting a root at -2 with multiplicity 1. And over here, by adding 2, we're getting one at +2, again with multiplicity 1. So both of these with multiplicity 1. So let's sketch that. Since all of the roots have multiplicity 1, they're all going to just pass through. So now we just look at the fact that we have an odd degree polynomial again, and our leading coefficient in this case is 1. So that's also positive. So we have actually a pretty similar looking shape as the last one, that it starts down low, but it passes through at -2, it passes through at 0, it passes through at 2, and then ends up. So both of these examples were fairly similar, but you could certainly try other functions just to get the idea of how this works. Okay, but certainly some of these polynomials, we're not going to be able to do this for everything. Like look at this next polynomial, for example. How on earth would we try to factor that, right? So you might think like, oh, okay, well, maybe we can factor by grouping and take x squared out of the first two terms and get x minus 1. But then there is no common factors for the next one, so we would just take out a 1. And so we don't have now a common factor to actually factor by grouping. So all the factorization techniques you've seen so far aren't going to help us. So in the next video, we're going to talk about how to deal with polynomials that don't factor.